Two very important yet widely misunderstood parameters which we will be considering in this video are the gate threshold voltage VGS-TH, the drain source on state resistance RDS on. Just before we get started, let's briefly introduce the MOSFET. The MOSFET is a three-terminal device used to switch or amplify signals, and it has pins as drain, source, and gate. MOSFETs, unlike the BJTs, are voltage controlled devices. They have an extremely high input resistance, so only a small amount of current can flow through the gate. MOSFETs can be classified into depletion mode MOSFETs and enhancement mode MOSFETs. Depletion mode MOSFETs are normally on, enhancement mode MOSFETs are normally off. So we can see their symbols. For the enhancement mode MOSFETs, if you look, we'll see we have disconnected lines here, representing the fact that the drain is disconnected from the source, showing that it's normally off. While in this case we have a straight line, which shows that the drain is connected to the source, showing it's normally on. So we have P-channel depletion mode MOSFETs, we have N-channel depletion mode MOSFETs, and we have P-channel enhancement mode MOSFETs, and we have N-channel enhancement mode MOSFETs. The depletion mode MOSFETs are less common. We have more of the enhancement types in use, and we'll limit our focus to the enhancement mode MOSFETs. For the N-channel type, drain current flows when a positive voltage above a threshold is applied. Note: threshold. While a negative VGS with respect to the threshold, if applied to the gate, will turn the MOSFET off. What is this threshold? Answering this question will bring us to the first parameter, gate threshold voltage. This defines the minimum gate to source voltage that must be applied to a MOSFET to create a conducting path between drain and source. But in reality, we ought to drive our MOSFETs with a voltage that exceeds the gate threshold voltage 2 to 3 times. So let's say we have the MOSFET IROF 3205, whose VGS-TH is 4 volts max. We should drive this MOSFET with a minimum of 8 volts to 12 volts. Ignoring this is possibly the reason your MOSFETs heat up in your circuits, you have partial conduction or no switching at all, and general reliability issues. Now, for the N-channel MOSFET, when VGS is greater than VGS-TH, our MOSFET turns on. If we have VGS approximately equal to VGS-TH, we're going to have weak current flow between the drain and the source, and we could have partial conduction. When we have VGS less than VGS-TH, our MOSFET is off. Now, there are logic level MOSFETs which have their VGS-TH at around 2 volts max, which makes it okay for them to be powered directly by the Arduino or microcontrollers, since they can supply up to 5 volts, and some of them are the IROLZ44N, the IROL3705, and the IROL540N. The easiest way to spot these transistors is by the L written in their part number. So once we see an L in the part number, we know these are logic level MOSFETs. So we look at the second parameter, which is the drain source on state resistance. Now this is the drain source resistance when the MOSFET is fully turned on. RDS on matters a lot in design because of losses. We know energy losses are a major source of heat. So if we have to use MOSFETs to switch high current loads efficiently, RDS on must be low. Otherwise, the square of the current going through the drain multiplied by the RDS on will give us the amount of energy we will be converting to heat. We will most likely have to use a large heat sink. Also, there will be a loss of voltage or a drop in our load voltage because of the voltage drop across RDS. Now, how do we ensure we have a low RDS? First of all, a high VGS effectively gives us a low RDS on. Also, proper heat dissipation would help us get a low RDS, because heat increase equals increase in RDS on. Then ultimately, it's the responsibility of the designer to pick MOSFETs with appropriate RDS on values and then work around that.